So it takes very long to evolve this system in space. So this is where statistical mechanics comes in. So let us look at two phase points, x1 and x2. Now each of these is essentially a collection of the positions and velocities of all the particles in this box, for example. Now from the point of view of the macroscopic observable, there is no difference between x1 and x2. Therefore, because these two microstates essentially lead to the same macrostate, so a single system which is evolving in time can be replaced by a collection of identical systems, or microstates, and this collection of identical systems is what Gibbs called an ensemble. Under this treatment, the average value of the macroscopic observable is its instantaneous value for a given set of positions and momenta, multiplied by a probability density function, and we will define this in a little bit. And this whole thing is integrated over the entire phase space. So this is the average value of this observable A, which depends on the momenta and the position of all particles. What is this probability density function? To understand this, let's go back to calculating the mass of an object. Let's say you have a three-dimensional object here, which is very dense in some parts and not so dense in other parts. So the density is not constant throughout. So if you were asked to calculate the mass of this, you would integrate over x, y, and z. And the density then depends on the position. In the case the density is constant, this density comes out, and then the mass becomes the constant density multiplied by x, y, and z. This is equal to rho multiplied by volume. This we know very well. Similarly, the rho defined here is a probability density. Just like the rho here is a mass density, the rho here is a probability density. What does that mean? So let's try to depict my phase space under two dimensions. So this is my 6n dimensional phase space. On one axis I have all the momenta for all n particles, and on the other axis I have all the positions. Each point in this two-dimensional plot is a point in phase space. So a collection of the momenta and positions of all the particles of the system. I can choose an infinitesimal volume here, and this volume is equal to dPn dQn. Just like for volume, when we were calculating mass, the infinitesimal volume is dx multiplied by dy multiplied by dz. Similarly, an infinitesimal volume here is dPn dQn. And the probability of finding my system in a region R at a given time t, this could be my region R for example, is given by an integral over the region R of the probability density function for a given time integrated over this infinitesimal volume. So this is very much equivalent to calculating a mass from a mass density. Now If n, the number of particles, the volume of the box, and the temperature are kept constant, then it can be shown analytically on pen and paper that the probability density function is equal to the exponential of the Hamiltonian, which we have already seen, divided by the Boltzmann constant multiplied by temperature. And in the denominator, we have the same term, but now integrated over the entire phase space. So you have the Hamiltonian divided by the Boltzmann constant multiplied by the temperature, and then integrated over the entire phase space. The quantity in the denominator, which we will call Q, is called the partition function in statistical mechanics. And from this partition function, one can calculate several thermodynamic properties. Based on this treatment, the average of any observable A, as we have already written above, is equal to its value for a given set of momenta and positions multiplied by the probability density function integrated over the entire phase space. Okay, it turns out that if one can calculate Q here, one can calculate the Helmholtz free energy. And I'm going to call it AH to describe Helmholtz and to distinguish it with A, which was any observable. And this is equal to minus Kb, Boltzmann constant, temperature multiplied by the natural logarithm of the partition function. So in order to calculate any thermodynamic variable, we need to first write the Hamiltonian, then we calculate Q, and from Q one can calculate all the thermodynamic quantities you need, such as temperature, pressure, enthalpy, Gibbs free energy, the heat capacities, and the Helmholtz free energy, and so on. It turns out that in practice, one does not need to actually calculate Q to calculate all of these. All right. So this average that we are talking about here for any macroscopic observable A is what is called the ensemble average, because it is obtained from the analysis of an ensemble of identical system. The ergodic hypothesis states that the ensemble average is the same as the time average, which we had considered earlier. And this is essentially what is done in molecular dynamics simulations. We take a system of interest, then we evolve it in time and we obtain a time average. And the ergodic hypothesis states that this time average is the same as the ensemble average. In the next lecture in class, we will discuss the basic principles of molecular dynamics.